Hello everyone, my name is Adnan Ahmed. I'm from University of Iowa, and today I'll be presenting our work on FlowTrace, which is a framework for active bandwidth measurements using in-band packet trains. This work was done in collaboration with folks from CAIDA, UCSD. So let's start. So to start things off, I'll talk a little bit about the background and motivation of our work. This will comprise of talking a little bit about the measurement tools and some of the prior research to optimize them and the limitations associated with it. So being a part of networking research community, we are very familiar with these questions. Answering these questions may help us make better decisions about the network. For instance, answering what the available bandwidth is may help a sender utilize the network better. Answering where the bottleneck links lie may help us identify where the root cause of congestion is. In this talk, I'll primarily be focusing on these kind of questions. So to this end, a significant amount of prior research has focused on coming up with measurement tools to answer these questions. These primarily fall into two categories. One is passive measurements and the other is active measurements. So passive measurements rely on monitoring ongoing traffic and local internal state to infer available bandwidth. They may use, for example, video playback buffer or packet arrival rate in the figure. For instance, if the video playback buffer is depleting fast, that indicates that the available bandwidth has decreased. So the main drawback of passive measurements is that they cannot detect when available bandwidth increases, as noted by prior literature as well. Active measurements, on the other hand, inject specific measurement traffic into the network and measure the network response to estimate available bandwidth. For instance, in this figure, we can see that the blue packets traverse the network along with the other packets as well. These packets signify the measurement traffic crafted by the end host, and they can be used to actively measure what the network is behaving. So there have been a lot of tools proposed in the prior literature that measure, for example, available bandwidth, where the bottleneck location is, by crafting different kind of measurement traffic. The drawback to these, however, is that measurement traffic actually ends up competing for bandwidth with the application traffic, thereby affecting the performance of the application traffic, and that it incurs additional congestion into the network as well, which may prove to cause congestion for other clients sharing the network. So in summary, the primary reason behind the drawbacks associated with active bandwidth measurements is that they transfer significant payloads over the network, and they're not actually transferring any useful information. Most of it is just dummy data. So prior research has explored the idea of actually leveraging useful application data to construct measurement traffic. In doing so, you are sending actual application data over the network to the other side, and you're conducting measurements at the same time. So this has been explored in prior research, namely MGRP and MinProbe. However, the primary problems associated with these solutions is that they require changes to the kernel, and they require specialized hardware, which makes them difficult to deploy in a wide-scale environment. So to go into a bit more detail of MGRP, the idea proposed by the authors was that we treat the probe packets as vessels, and we fill those vessels with the application data, thereby creating the measurement traffic, which is actually carrying useful data from one end to the other. And the receiver, whenever it receives these MGRP packets, it can demultiplex or extract the application data out of the vessel probe packets. It can send the application data to the corresponding application and then conduct the appropriate measurements. So this is a high-level overview of what MGRP is. You have these probe packets which are being generated by the predefined or user-defined measurement algorithm. The MGRP creates these probe vessels, which are filled by the applications which generate the application traffic. And by combining them, you have the measurement traffic, which is actually carrying useful payloads. These measurement traffics are being sent over the network to the other side. And at the other side, the MGRP, again, demultiplexes the probe packets from the application traffic, send the application traffics to the applications, and conduct the appropriate measurements. One of the issues, however, is that it requires changes to the Linux kernel, which may make it difficult to deploy at a large scale. So in a similar fashion, MinProbe was proposed by Wang et al. In IMC 2014. MinProbe is a middle box architecture that was proposed to conduct measurements at high-speed networks using application data. Specifically, MinProbe uses an FPGA PCIe pluggable board, namely Sonic, to access and modulate inter-packet timings with high precision by accessing idle symbols in the physical layer. This allows MinProbe to modulate application traffic at desired rates while measuring packet timings with a high precision as well, thereby allowing for accurate measurements in high-speed gigabit networks. This is a high-level overview of MinProbe, where the measurement algorithm describes how MinProbe should modulate the application traffic to construct appropriate measurement traffic, such as packet trains at the desired rate. MinProbe modulates the application traffic by adding or removing the idle symbols in the link. The gap extraction module, on the other hand, in MinProbe, counts the idle symbols to accurately measure the interpacket timings and thereby estimating the available bandwidth with high accuracy or high precision. The main drawback, however, of MinProbe is that, again, it requires specialized hardware such as Sonic, making it difficult to deploy in a general wide-scale setting.
So now I'll move on to describing our proposed framework FlowTrace. I'll go into the design goals and the framework itself, and then I'll also move on to describing one of the algorithms that we implemented in the FlowTrace framework called pathneck.
So first of all, I would like to highlight some of the design goals we had for the FlowTrace framework. First of all, we would like to be able to implement any kind of measurement algorithm we want using FlowTrace. By implementing FlowTrace as a user space program, we can do so by just modifying it and implementing the desired measurement algorithm. Secondly, we would like to not have any kind of specialized hardware requirement or kernel patch for the FlowTrace program. Instead, we would like to design FlowTrace by using any basic Linux utilities, which may come with any version of Linux, thereby easing the deployment of FlowTrace in the wild. Keeping the design goals in mind, our high-level design framework for FlowTrace is as follows. We want to allow for in-band implementation of different active measurement algorithms using application data to decrease measurement overheads. To this end, we first identify the flows we want to use for our measurement and intercept the packets from the flow from the kernel. We then collect these packets in the user space to generate measurement traffic according to the user-defined configurations. FlowTrace then waits for the specified number of packets to be received from the application flow. And lastly, FlowTrace constructs the measurement traffic and just transmits it over the wire at the desired rates in an in-band manner.
So with a high-level methodology in mind, I would like to go over some of the technical challenges we faced while designing and implementing FlowTrace. Firstly, FlowTrace is a user space program, which means that it does not have kernel-level visibility and packet control. That's why it cannot identify or intercept the packets from the flows that it wants to target. Secondly, the applications may not generate the packets at the rates we desire. FlowTrace wants to construct the measurement traffic and send the measurement traffic at the certain rate. So that's why we want to be able to control the transmission rates of the packets. And lastly, and I'll discuss this a little bit later in a bit more detail as well, FlowTrace may end up storing packets in memory and potentially causing some delays in the packets transmission as well, which can potentially lead to an impact on application performance. We want to minimize the impact on application performance as well.
So before I go into how we tackle the challenges we just discussed, I would like to take some time to discuss some of the tools and libraries we used in our implementation of FlowTrace. Firstly, we use iptables, which is a user space program to configure firewall, which means allowing or blocking application traffic by defining certain rules. Secondly, we used libnetfilterq and nfq. NFQ is an iptables target, which basically means that iptables matches a packet's metadata against some rules, and if the rules match, then the packet would be sent to this queue. Whenever a packet is sent into this queue, the verdict for this packet is delegated to the user space.
The user space programs issues verdicts using the API provided by the libnet filter queue library. So note that the user space is only aware, or the user space program is only aware of the head of the queue, which means that subsequent packets will not be sent to the user space until the previous packet has been issued a verdict. So whenever a packet has been issued a verdict, it is popped from the queue and the corresponding action is enforced. So packet buffering is an action in which we buffer packets in user space. Whenever a packet is received by the NF queue, we send the metadata and the packet payload to the user space, and the user space drops the packet or asks the NF queue to drop the packet and buffer the packet in user space along with its metadata and the payload. So based on this discussion, we solve these challenges as follows. We get over the issue of lack of kernel level visibility by intercepting packets by configuring IP table rules and intercepting packets using these rules via NFQ. To control the transmission rates of the packet, we buffer the packets in memory. So whenever a packet is received by the queue, we ask the queue to drop the packet. We record the metadata of the packet into the user space, and so that we can later respawn these packets or transmit these packets at whatever rate we desire. And lastly, to minimize the impact of FlowTrace on application performance, we maintain per packet wait timers to avoid latency overhead. So basically, whenever a packet is received, we wait for a small period of time, and if in that time another packet is not received, we do not do the measurement and we just send the packets right away. Now that we have a high-level overview of how FlowTrace is designed and implemented, I would like to take some time to describe pathneck, which is the algorithm that we implemented in FlowTrace. Pathneck was proposed by Hu et al. In SIGCOMM 2004. It's an active probing technique which locates choke points and bottlenecks, the bottleneck being the last choke point along an internet path by constructing a specific measurement traffic. So the measurement traffic that it uses is called recursive packet trains. It consists of load packets and measurement packets. So this is what the measurement traffic looks like. It's a recursive packet train looks like. It's some measurement packets at the edge of the train. These measurement packets are very small, TTL limited, which means that as you go towards the edge of the train, the TTL is decreasing to 1. And enveloped by these measurement packets are the load packets, which are the large payload packets. And this whole train is sent into the network by the pathneck program. And it locates the choke points by measuring gap values in the returning ICMP messages. So whenever this recursive packet train traverses a router, all the TTL values are decreased by 1. So the edge packets, edge measurement packets, which have the TTL 1, their TTL would decrease to 0, which means that there would be an ICMP message sent back to the sender notifying it that the packet was dropped. So the sender pathneck program would actually use the timings of the reception of these ICMP messages to measure the gap values, and by using an algorithm, they identify where the choke points are. So naturally, since the load packets are the large packets, these are the cause of the problem for pathneck. They are the reason for the high congestion overhead for the algorithm. So in this implementation, we use application traffic as the load packet substitute in the recursive packet train. So this is what a high-level implementation of pathneck in FlowTrace looks like. We have FlowTrace, the user space program running alongside the applications. We first identify the flow, whichever one we want to capture, and we then configure the firewall using IP table rules, which tells the firewall to look for the 5-tuple of that flow and send the packets to the NF queue as the target. Whenever the application generates the application traffic, this application traffic is intercepted by the firewall, and the firewall sends all these packets to the NF queue. The NF queue tells the user space program that a packet has arrived in the head of the queue. The user space program drops the packet using the verdict NF drop, and then it copies the packet into the Ethernet, the whole Ethernet packet into the user space memory. And this keeps on going until we have received the end packets from the application itself. And if we do end up receiving the end packets before the timer expires, we construct the recursive packet train. We add the TTL limited probes before and after the load packets, and we send this train out over the wire using PCAP handlers directly over the wire. If we end up not getting enough packets, or if the timer expires, for example, we just send the packets without any probes directly over the wire to minimize the impact on the application performance. And once all of the measurements are done, we can just delete the firewall rules and the application traffic would flow as if there was no interception at all. So now let me move into the evaluation section a little bit. Our evaluation tries to answer the following questions. The first question we ask is, are the measurements done with pathneck implemented on FlowTrace closely follow the measurements done by the original pathneck without any FlowTrace? The second question is that if we have cross traffic along the network, how does it affect the measurements done with both pathneck and FlowTrace? And lastly, we want to see what kind of latency overheads we see whenever we try to intercept the application traffic. We buffer the application traffic in the user space for some time, and because of that, there must be some additional latency experienced by the application. So we want to quantify what kind of overheads exist in that domain. So we conduct our evaluation on an Emulab testbed, which is a network testbed comprising of rich PC clusters. The topology that we used for our evaluation is a linear topology, which is basically two hosts connected end-to-end via a bunch of routers. We vary the bottleneck location to generate different scenarios, and we vary the bottleneck size as well. We have one background flow running from one host to the other. This is the application flow that I was talking about earlier. And in order to quantify the second question, which is how does cross-traffic affect our FlowTrace and pathneck without FlowTrace, we generate different cross-traffic scenarios as well. So we measure the gap values with both pathneck and FlowTrace, and we compare to see how they fare against each other. So in the first scenario, we generate this two choke point scenario in which there are choke points at hop 2 and hop 3. Hop 3 being the last choke point would be the bottleneck link as well. We have again with and without cross traffic scenarios, and we measure the gap values with both pathneck and FlowTrace. So without cross traffic, this is how pathneck measures the gaps along the path, end-to-end path. And this is what FlowTrace measurements looks like. So we see, first of all, that both pathneck and FlowTrace measure similar gap values across the hops. They are very closely agreeing with one another. Secondly, we see that the gap values increase at hop 2 and at hop 3, indicating that hop 2 was the first choke point and hop 3 was the second choke point. The errors in the gap values are low for both FlowTrace and pathneck. This is because this is without cross traffic. We expect there to be very little variance in the gap values measured by both techniques. So with cross traffic, we see that both pathneck and FlowTrace measure similar gap values. Again, the median gap values are similar across all the hops. We see that both pathneck and FlowTrace report the same hops as choke points. However, we do note that the variance in the measured gap values increases as we go along the path. This is the case for both pathneck and FlowTrace. So we create another scenario called 3 choke point scenario, in which we have choke points at hop 3, hop 6, and hop 8. Hop 8 being the last choke point also is the bottleneck link. We again consider scenarios with and without cross traffic, and we measure with both pathneck and FlowTrace. So without cross traffic, pathneck indicates that the gap values increase at hop 3, hop 6, and hop 8. FlowTrace, again, in this case as well, has measurements which closely agree with those done by pathneck. So this is as expected as before. We see that pathneck identified hop 3, hop 6 and hop 8 as choke points because that's where the gap values increase significantly. And this was measured by FlowTrace as well. So both will give you same information. And again, in this case, without cross traffic, the gap values experience relatively low variance across the hops. So with cross traffic, again, we see that both pathneck and FlowTrace measure similar gap values across the hops. Both of them report hop 3, hop 6, and hop 8 to be the choke points. And in this case as well, we see that the errors increase across the hops for both pathneck and FlowTrace. So we now move towards understanding the latency overheads introduced by FlowTrace for the applications to quantify if an application performance may be impacted by FlowTrace or not. So to this end, we measure whatever additional latency each application packet may experience because it has been buffered by FlowTrace. What we do is we measure the time whenever a packet is delegated to the user space, and we measure the time that it was actually sent out of the machine. So this time gap would quantify how the additional time that the packet had to wait in the user space in order for the measurement traffic to be constructed. And then we study the effect of the per packet wait timers on these latency overheads to see if by configuring different per packet wait timers, do the application performance get impacted or not. So this is what the latency overheads for different packets from the application traffic looks like. On the x-axis, we have the packet IDs from the application, and on the y-axis, we have the latency overheads experienced by each of those packets. So this curve is for a per packet wait timer of 250 microseconds. We note that the overheads exhibit a sort of a periodic pattern where there is a rise and then it decreases and then there's a rise again and then it decreases again. The reason is that whenever the first packet of the application arrives in the NFQ and does get copied into the user space, it has to stay there and wait for all the end packets from the application to arrive. And whenever the last application packet arrives, the measurement traffic or the recursive packet train is constructed and sent right away, which means that the first packet experiences the most overhead out of all the packets. And this repeats across different iterations of the recursive packet train. So now we change the per packet wait timer for different values, and we see that as the per packet wait timer threshold increases, packets can potentially be buffered for longer and they may increase the latency overheads experienced by the application. However, in the worst case scenario, we see that it is still less than 1.5 milliseconds. And this may happen when, for example, the application has not sent any packet, so it waits for a long time before for a packet before it decides that I just need to send the packets out. In our studies, we see that the latency overheads vary from 0.75 milliseconds to 1 milliseconds for different values of TIPA. So in this talk, I presented FlowTrace, which is a framework to allow for an in-band implementation of the active network measurement algorithms proposed in prior literature. We implemented FlowTrace using basic Linux utilities. We do not require any changes in the Linux patch, in the Linux kernel, or any specialized hardware. Therefore, we can run and deploy FlowTrace on any commodity hardware, and thereby allowing for wide-scale deployment. We implemented pathneck in FlowTrace and showed that the measurements conducted by both FlowTrace and pathneck closely agree with each other. They measure the same gaps across the hops for the ME-Lab testbed that we had created, and they identify similar choke points. Lastly, we showed that the latency overheads are relatively minimal whenever FlowTrace is run, so the application performance is minimally impacted. However, we also showed that the latency overheads may increase as you increase the value of TIPA, the threshold for interpacket arrivals. This acts like sort of the timeout value in TCP, where if you have too small of the threshold value, you won't be able to conduct any measurement anytime. If you have too large of the value of this threshold, then you would probably wait for a long time before you'll realize that the application is not sending any packet, thereby impacting the application traffic a lot as well. So as part of our future work, we want to implement other measurement algorithms proposed in prior literature, such as path load, path chirp in FlowTrace, and see how they fare against their FlowTrace implementation. We want to conduct internet-wide experiments using these algorithms implemented in FlowTrace, and the idea being that a server can run FlowTrace and it can conduct the measurements to the downstream ASs, for example, while sending useful traffic to them as well. And we want to study the impact of FlowTrace on different kinds of applications. So for example, how web browsing may be impacted whenever FlowTrace leverages its data for its to conduct measurements. So with that, I would like to conclude my talk. I would welcome any questions. Thank you so much for listening.